Alrighty, let's get back to this velocity addition formula. So this works great in Galilean relativity. That means when the speed of the object is much, much less than the speed of light, it works great. But as we learned earlier, it does not work when you're talking about things moving at relativistic speed. So what we'd like to know is what's the correct equation. So that's what we'll deal with now. We'll learn how to add velocities correctly when an object is moving at relativistic speeds. Okay, so, I already said that. So this is just review. So this is physics 121, right? The Galilean transformations, which like I just said, that work great when objects are moving slowly compared to the speed of light. These are the Lorentz transformations that we talked about earlier. Einstein derived these. And again, he was surprised to learn that Lorentz had already done so. But again, Lorentz didn't follow through, you know. He just go to stop. Einstein followed through and discovered relativity of space-time, et cetera, et cetera. So these work with mechanics, with electricity, magnetism, everything. These work. These transformation equations work. And like I told you earlier, they indicate that time is relative, that distance is relative, all that good stuff. All right, and don't forget the v here is the velocity of the s prime reference frame relative to the s reference frame. And of course gamma depends on the v, right, because gamma is in terms of beta. Okay, so what's in yellow, these are the deviations from the Galilean relativity, right? You don't see any, right, there's no gamma, right? There's, you know, Galileo and Newton, they say that time is time, and of course we know differently now, right? So this, okay, now how do you go from this to velocity? You take the derivative. So and I'm skipping a lot of algebra, but basically this is the Galilean equation that I just discussed, which I just showed you. And this is the correct equation. So look, the numerator, same thing, right? This is the only thing that's different, just this denominator. And look at the denominator, you know. 1 plus these velocities squared divided by c squared. So if these velocities are small, I mean c is huge, so c squared is even huger. Is that a word? I don't know. So this divided by c squared for non-relativistic physics, this is 0, right? This only gets large if we're dealing with relativistic speeds, all right? So there it is, whoopee, all right? So same equation, just new denominator. All right, so let's do this problem. Now, I think that the easiest way to do these velocity problems is just to use that formula we learned in physics 121. So that's what I'm going to do. I think it's much, much easier than most methods that are taught in the books. So let's just try to do it the easy way, all right? Okay, so here's a complicated problem, right? So here's Abe, and then B, I guess B is moving relative to Abe, and then B shoots out a probe. So look at it. This is the velocity of the probe relative to B. This is the velocity of B relative to A, and this is A. Woo! So there's all sorts of crazy things going on, right? All right, so find the velocity of the probe relative to Abe. So again, just do what we did in physics 121. Velocity of the probe relative to A. So just remember. Okay, P on left, P on left. A on right, A on right. And what's the only other reference frame? B, right? B. So that's not so bad. And again, you know, these are vectors, right? They're vectors. Okay, so that's what I would do. Makes it easier that way. All right, so here's what we've learned in 121, what I just wrote there. And what we have now, this is 121, Now we just have this new denominator. The new denominator is just 1 plus that multiplied by that divided by c squared. Now be careful. Sometimes these might be negative, you know. So you just got to watch the signs, all right? So I mean, if one of these is negative, that means that this thing is going to be negative. So just be careful. Okay, so that's all you'd have to do. Just use that simple equation, which is very similar to what we learned in 121. Okay, what do you say we actually do one? Let's do a problem. Okay, rocket ship A. So rocket ship A is moving away from Earth at 0.6 c in the x direction. So velocity of A relative to Earth is 0.6 c. All right, that way. Rocket ship B is also moving away from Earth, same direction. So VB, Earth. Oh, wait a minute. Rocket ship B is also moving away from Earth in the same direction and is moving at a velocity of 0.5 c as measured by A. Okay, woohoo, almost got that wrong. So velocity of B relative to A is 0.5 c in the same direction. So we don't have to worry about minus signs. How fast is rocket ship B moving in Earth's reference frame? Okay, there you go. So, physics 121, right? Velocity B blank plus velocity blank Earth. The only other reference frame is A, right? And then it's just 1 plus that multiplied by that over c squared. That's all. Now what's cool about it though, let's see, okay, remember this is the relativistic addition, or the new part. So let's do the, okay, what's the numerator? The numerator is 0.5 c plus 0.6 c, which is 1.1 c. So if we didn't have relativity, I mean this is what Isaac Newton would say, right? Isaac Newton or Galileo, they would just say 1.1 c. But now we have this new denominator. So now we say 1 plus 0.5 c times 0.6 c over c squared. And I promise you when you do that, you get 0.85 c. Okay? So there you go. So basically, when you have this denominator, you can never have anything exceed the speed of light. So that's another premise of relativity. Nothing can travel faster than the speed of light. So I encourage you to come up with some examples and prove it to yourself. You know, use this formula and just prove it to yourself that I don't care how fast things are going. I mean, you know, less than or equal to the speed of light. Nothing can travel faster than the speed of light. So what am I saying? So I'm saying, like, let's say I have your rocket here. Let's say that's going 0.999 c, and then it emits light, which is going c. So figure out here's the Earth, and so figure out the speed of this light relative to the Earth. I mean, Isaac Newton would just say that plus that, which is 1.99 c. Right? That's what Isaac Newton would say. But do it using the equation. You'll see it'll come out to be c, because everybody measures the speed of light to be the speed of light. So just have some fun with that equation, see what you come up with. Okay, very good. All right, let's talk about momentum. Momentum. So again, just going back, using that velocity equation that we just learned, nothing can travel faster than the speed of light. Nothing. And I want you to prove that to yourself, right? Just try some examples. Okay. So classical physics, this is what we learned. Remember, u is the velocity, right? So classical physics, p, momentum equals mass times velocity. And of course, velocity is delta x over delta t. Now, relativity says we have to change. We have to modify the equation. Why do we have to modify the equation? What's wrong with that? Well, think about it. Relativity, special relativity, says that the speed of an object has to be less than or equal to c, right? Now, classically, there's no limit. This can be as big as you want, correct? But we know from relativity that u has to be less than or equal to the speed of light. Well, so we have to somehow incorporate that into this equation. So we've got to change it, okay? So that's one argument, right? That's one argument why we have to change the equation. The second argument just is look at the data, I mean, okay, again, classically, P equals mu. Don't forget, u is the velocity. So therefore, we say that P is proportional to u, right? So they're linearly related, right? They're linearly related. So this is what Newton would say. So let's say you plot P versus u. Well, you're going to get a straight line, right? If P is proportional to u, you plot P versus u, you get a straight line. So this is the Newtonian momentum, right? However, relativity says, sorry, you can't have a speed greater than the speed of light. And so when you actually do the experiments and you measure P versus the speed, it goes like this. Whoop. All right? Which is obviously not a straight line. Okay? So all I'm trying to say is we have to change our equation for momentum. Now again, when you're dealing with things moving slowly compared to the speed of light, P equals mv is fine. It's only when you get these really, really high speeds that you have to change your equation. Okay, so I'm just going to give you the result. So this is the equation for relativistic momentum. Here's the mv, or the mu again, but now we have to multiply by gamma. Now, notice I put a little p here, and I put it in green, so I'm kind of making it stand out. Okay? This is kind of a big deal. Gamma p is the gamma factor for the particle, not for the reference frame. So just be aware of that, right? Usually we figure out the gamma for the reference frame, but this is the gamma for the actual particle, whatever's moving. So just be careful about that. Yeah. Okay. So this is so here, it's gamma, right? So it's one, same equation as before, but now u is the velocity of the particle moving in the reference frame. Okay, it's not the velocity of the reference frame. Now, this is really kind of awesome. So this is Fermilab. I've already told you that. And again, Fermilab, what they do is they make protons go around and around and around, and they go faster and faster and faster, and then they collide with something. Now, protons don't want to go in a circle, right? Protons, like anything else, wants to go in a straight line. And so what they use at Fermilab to make them go in a circle is they use magnets. So we learned in Physics 220 that there's something called a magnetic force, and it changes the direction of a moving charged particle. All right, so when you look at Fermilab, if you look inside the beam tunnel, just magnets almost everywhere, just to make those protons bend. Now, classically, if the momentum rises like this with the speed, right? And so think about it. So classically, as the momentum increases, you get the people at Fermilab, operators, they have to increase the magnetic field, because the larger the momentum, the more the proton wants to go in a straight line, Okay, so as the proton goes faster and faster, you have to crank up the magnets. Well, if they use this line, they would lose all their protons, because you have to use the relativistic line. So basically, when the protons start going, like, have speeds like around here, they really have to crank up those magnets to make those protons go in a circle. Okay? So I guess that's another proof of relativity, that you can't use this. It doesn't work. You got to use that. All right, a 1 times 10 to the minus 6 kilogram particle moves at 0.25 c. What percentage error with the class, what's supposed to be with? Oh, no, I guess will. Will the classical expression for momentum give? Yeah, so fine. In other words, what's gamma, right? What's gamma p? Because, Gamma P is the difference between the classical and the relativistic equation, you know? Okay, so everybody please pause your video and figure out gamma P. All right, so we're back. I hope you did it. So gamma P is equal to 1 minus beta P squared negative 1/2 power 1 minus 0.25 squared minus 1/2 power 1.033. All right. So what's the answer? 3%. Okay. Yeah. Okay, so that's relativistic momentum, and they use it in particle physics labs every day. So it's crucial. We haven't talked about energy yet. If you remember 121, I did tell you that energy is conserved, period. Quantum mechanics, relativity, everything. Energy is conserved. So we want to go through this, and what we're going to discover is Einstein's famous equation, E equals mc squared. So that's pretty important, so we want to talk about it. Okay, woohoo! Conservation of total energy. So what we want to talk about is consider a relativistic particle. So that means that the kinetic energy is so much greater than the gravitational potential energy. We're just going to ignore the gravitational potential energy. And that's totally fine because it's negligible. Okay? All right. Well, you know, here we go. So typically we have energy is kinetic plus potential. And we just said that the kinetic is so great, we're going to ignore the potential. So the energy is just kinetic. Now, you have to admit, I mean, classically, kinetic energy is 1/2 mv squared. Well, classically, there's no limit on this. But in relativity, we have to limit that v, right? It has to be less than or equal to c. So you know this equation has to change. We have to modify it. It's not going to be simple like it was with momentum. Oh well. All right. So I'm not going to show you every single step. I'm just going to kind of hand wave. Okay, so we start off with something that we know is true, this invariant. So the space-time interval in one reference frame equals the space-time interval in another reference frame. Okay, that's cool. We believe it. And then we do a whole bunch of math, which I'm not going to show you. It's in the book if you really want to see it. So this means a whole bunch of math, right? All right. So we do a whole bunch of math and use a lot of substitutions that we learned earlier. And we come up with an invariant mc squared squared equals this, gamma p mc squared squared minus pc quantity squared. All right, fine. All right, so this is an invariant, yeah? So therefore, we can say that this in one reference frame equals this in a second reference frame. So here we have it in one reference frame. Here we have it in the primed reference frame. Okay, great. Wonderful. Now, this is fine. This is the momentum. That's the speed of light. Okay, I know what that is, but what's this thing? What's gamma mc squared? What is that? So that's what we want to discuss, okay? And we're going to learn something. So what in the world is gamma p mc squared? All right? Now, one way to figure these things out just by looking at the units. So let's just look at the units. That never hurts. So let's just look at the units. All right, so gamma is a number that has no units. M is kilograms. And then c squared is meter per second squared, right? Okay, well, that is a kilogram times a meter per second squared times a meter. Agree? And you better know this by now. What's a kilogram times meter per second squared? It's a Newton. So we have a Newton meter. And what's a Newton meter? It's a joule, right? Which is a unit of energy. So that means that this thing is energy. Wow. That's weird. mc squared is energy. Okay. Now we're going to do the, okay. But come on, that's just hand waving. Now we want to do it the real way. All right? So we're going to take a situation where U is much, much less than C. You'll see why. Okay? So let's just work out what this crazy thing is. Okay, so gamma P mc squared. All right, well, what's gamma? 1 minus beta squared negative 1/2 mc squared. Okay, what's that? That's 1 minus, okay, watch it, yeah, U, sorry, U over C negative 1/2 mc squared. All right, right? Because U is the velocity. Okay. Okay, now, remember, I'm saying that U is much, much less than C. All right, so that we can use that, remember that? We had 1 minus x to the negative 1/2 equals 1 plus x over 2. Remember that? That was that thing that we learned with the binomial theorem. You know, if this x is much, much smaller than 1, well, we have it, right? U is much, much less than C. So this is much, much less than 1. So we can just say, we can just use that equation. We can just say this is 1 plus U squared over C squared divided by 2 times mc squared, right? So this here, we're just going to use that. That's going to be 1 plus this divided by 2. Okay, but it's still times mc squared. So then we're going to get mc squared plus mu squared over 2, right? Multiply that out. That times that is that. That times that is that. Now, that's cool. What is this? This is 1/2 mass velocity squared. What's that? That's kinetic energy, right? That's kinetic energy. Well, what's this thing? I mean, it has, I mean, it's, look at it. We know it's going to be energy, right? But come on, it has a mass in it. So, you know, this is some kind of rest energy or something like that. So we're going to call it rest energy, right? Because it just has that mass in it. So therefore, there's a kinetic energy and there's a rest energy. So what's this? It has to be total energy. What else could it be? I mean, look at, there's no gravitational energy. It has to just be total energy. So, all right, so gamma mc squared is the total energy. But look, in order to say that, we've kind of invented a new kind of energy, right? Something called rest energy, you know? That's all right, we can do it. Okay, so that was our question, and we learned that this gamma mc squared is the total energy, All right? Woo! Okay, so here you go. So for any particle, the total energy is the rest mass, or the rest energy, plus the kinetic energy. So this is the new thing that relativity comes up with. Okay, rest energy. Okay, so we have E total equals E0 plus K. All right, now, once again, what is E0? It's mc squared, right? It's mc squared. Okay, so therefore, what is the relativistic equation for the kinetic energy? We'll just use this, right? So the kinetic energy, therefore, is E tot minus mc squared. But wait a second. This is E tot in the blue. So we have gamma P mc squared minus mc squared. Well, factor out the mc squared. you get mc squared gamma p minus 1. So that is the kinetic energy. Sorry, right? So now you have some new terms, you know? So this is the rest energy, mc squared, brand new, thanks to relativity. Now we have this brand new expression for kinetic energy, mc squared gamma p minus 1. And this is going to limit the velocity to being less than or equal to c. So we've kind of killed two birds in one stone. All right? So there you go. So this is all new, right? This is relativity, you know. And this thing here, this is what we got after we did a lot of math, which we didn't do, right? mc squared is E0, right? So this is E0 squared. What's this? This is E tot, so we have E total squared. So we can just write this equation differently. This is E0 squared equals E total squared minus PC total squared. This is just another one of these equations that you get in relativity that sometimes you just need to solve problems. So you just want to kind of keep this in the back of your head, all right? Okay, so there you go. There's all the new equations that we came up with energy. This is the total energy equals the rest plus kinetic. That's the rest. That's the kinetic. Then we have this other thing that's semi-useful. Now, here's the fun stuff. Remember, energy is conserved. Energy is constant. So this E total, which is gamma mc squared, equals 0 plus k, it's constant. No matter what, it's constant. So you say, who cares? Well, you watch. Okay, so what does it mean? Well, you know, again, the E total is the rest plus kinetic. So let's write it differently. Let's just say this. So the rest plus kinetic initially equals the rest plus kinetic final, right? That's what we learned in 121, energy conservation. You know, so I don't care. This quantity will never change, no matter what. It will never change. So, all right, let's write it in a different way. So E0 is m initial times c squared plus k initial. That equals m final c squared plus k final. Okay, when you write it like that, you know, what does this imply? Here you have subscripts on the mass. Well, that implies that the mass can change, right? So what does that say about conservation of mass? Mass is not conserved, right? Mass by itself is not conserved. So when you're told conservation of mass in your high school chemistry, they lied, because mass is not conserved. And I'm going to give you some examples of that later. Okay, let's quit.